This video is a conceptual and semi-mathematical exploration of the impulse momentum theorem. Yeah, let's see how this goes. I'm going to start off really quick saying some of the things. If you're just watching the playlist, you would not be surprised by what I write down, but I'm going to kind of write down some summary things about the impulse momentum theorem. So the theorem itself, all it says is this: if you can figure out how to calculate what's called the impulse by the net force on an object, you are guaranteed that that is equal to, it has the same value as, the change in the momentum of that object. This is what the theorem says. On the side, the impulse is a vector, and it's calculated by asking what is the integral of the net force acting through small time increments. And this makes it so you can think about forces that might change in time, including direction. So not only the strength, the number of newtons, but also the angles that specify the direction of the force. And this net impulse goes on between the two times t1 and t2. Yeah, and it's made out of the net force acting on the object. If you want to, you can also just calculate the impulse delivered by any particular force. So I just use this character a to specify that we're talking about a force called F sub a, and it's just the integral of the force vector a dt. But this is not delta p. It is not the impulse momentum theorem. The impulse momentum theorem is there is a resulting change in momentum because of a net force acting for time. Please be careful about that. This is not delta p if F sub a, this force, is not the net force. That's maybe a better way to say that. Okay, so this is all well and good. So this is the impulse momentum theorem, but I'd like to think about delta p, and it's going to, let me do this. So delta p is, this is how you define it. It's p final minus p initial. And actually, maybe I should go and, if I define the net impulse as going from t1 to t2, maybe it's better. I'll do it this way for now. This is the momentum at the end of the time interval, and this other thing is the momentum at the beginning of the time interval. And the impulse is what causes the change. This is the change here. So, I'm sorry it's becoming a little bit messy looking, but this is what it looks like when you do stuff on paper. So p sub 2, I'm going to solve for p sub 2. This is a vector equation, and it's actually a vector definition. It's the definition of what's meant by the change in p. But I'm going to solve for p sub 2. P sub 2 equals, so this definition implies that p sub 2 is equal to p sub 1 plus the change in p. Do you see how that works? I just add p1, the vector p1, to both sides. That's what I get. I really like this description of momentum changing. The idea is if you have a starting value of momentum and then it changes by this amount, then the starting value plus the change is the finishing value. And the impulse momentum theorem, another way to write it, so I'll do this little double arrow. It just means that they're sort of the same statements. You can say that P2 is equal to P1 plus the impulse delivered by the net force between the times 1 and 2. I think this is a nice way to write the impulse momentum theorem. This right here, this is just, this is the definition of change. If you have a start value of whatever, including vector whatevers, and you have a change of this amount, then after the change you have this new value, right? But this is what the momentum impulse theorem is about. Okay, so next thing I would like to, just as a small aside comment, kind of, it's hard to think in terms of vectors and think in terms of an integral of a particular function that may be a complicated vector function of time. This is all sort of complicated. So in order to sort of think about stuff, and kind of be hand-wavy about things, it's helpful to define what's called the net average force. And notice that I'm going to drop the vector symbol. This is just us thinking. It's kind of a semi-mathematical way of thinking, but really it's semi-mathematical, but it's very physicsy. So there is some sense of an average value of the force. So let me draw a picture of a force that's changing in time. Here is a force whose value is changing in time, right? So here is f as a function of t, right? And it's this kind of crazy function. It gets big, then small, then comes up, but then kind of relaxes and then gets strong again. In some average sense, there is a value that represents the force over the time. So we could say that this level, this dashed level, is sort of the average value of the force. The force function spends, you would say, equal amounts of time above and below this average value. So the impulse can be thought of as just the net average force, so just this dashed line value, right, which is a constant, multiplied by the time interval that you're thinking about, the one going from t1 to t2. And this is kind of like a sort of a way to think about stuff. I'm going to give you an example where it's going to be obvious that a force has to change in time, that it and it will make sense. But this is a nice kind of like semi-mathematical, very physicsy way to think about impulses building up, because some sort of constant-ish average value of force acts over a time interval. And this is what I'm going to think conceptually with. It's hard to think conceptually with all this stuff. So let's go and do some simple hand-wavy thinking with this kind of idea. And so, okay. So before I move on, I want to give you a clue, because you might be able to sort of like pre-guess where I'm going with the conversation. I want to say injuries and damage are not because of large impulse. Injuries and damage are because, so I'll put but. So injuries and damage are not because of large impulse, but because of large force. This is something to keep in mind. So let's see what this has to do with thinking with impulse.